This is my last video for standing waves. This one, if you notice, has like 1/4. There's going to be 3/4, 5/4 wavelengths. So this one actually follows a slightly different pattern. It's going to be 1 times the fundamental, 3 times the fundamental, 5 times the fundamental, right? So it's because of its asymmetry, because it's closed at one end, open at the other. We actually are going to skip the even number of multiples. It's always the odd multiples. It's weird. You'll see. Okay, so it's the same thing. This length here is 1.715 meters. Okay, whatever this is. Look how good I am at drawing straight lines. Okay, and then the speed is going to be the speed of sound. So this is actually a panpipe, uses one end fixed, right? So the air, or if you blow into a soda bottle and make it sound like that, the air just moves in and out. Right, organ pipes. There are some organ pipes that have one end fixed and one end open, like this. Okay, so so let's see, displacement of the air. So let's do this. This is 1/4 wavelength. So I go 1.715 meters is 1/4 wavelength, right? So therefore the wavelength is, well, 4 times that, right? So 4 times 5 is 6.86 meters. Right, and then for this guy, we're going to use this formula, right? So frequency is always v divided by wavelength, right? So the frequency is the speed of sound, right? Because this is a sound wave, okay? So 343 meters per second divided by 6.86. So 343 divided by the answer I just got is 50. Right, so if you recall, when we had a pipe the same length with both ends open, the frequency was 100. If you close one end, you can get an octave lower. So the really, really low notes on pipe organs, the pedal tones, right? They either have to have pipes that are huge, right? Or they can actually fit just 1/4 of the wave in the pipe, right, and get an octave lower. And when you see those in churches, those are the ones that have the little sounding hole on the top. The ones that have the sounding hole in the bottom are the ones that are both ends open. Okay, so 50 hertz, that's a good low pedal tone there, right? Now here we've got 1, 2, 3/4 wavelengths, so 1.715 meters is 3/4 wavelengths, right? So therefore 1.715 times 4 divided by 3. The actual wave is 2.28666 meters, right? So our frequency is 343 meters per second divided by 2.286 repeating, right, meters. Okay, so 343 divided by second answer on my calculator, 150 hertz. Okay, so now this is, aha, suddenly there's something interesting or different, right? This is 50, this is 3 times the fundamental, right? So this one is going to go 1 times. This is going to be 3 times. What will this one be? Will this one be, 9 times? Is it multiplying by 3? No, it's going to be 5. I'll show you. Okay, so how many quarter wavelengths? 1, 2, 3, 4, 5 quarter wavelengths, right? So 1.715 meters is 5 quarter wavelengths, right? So lambda is slightly smaller than that, right? 1.715 times 4 divided by 5 is 1.372. Somewhat surprisingly, it comes out even, right? So our frequency is, because it's still a sound wave, right, 1.372. So 343 divided by my answer is 250. Right, so the pattern is 1 times the fundamental, 3 times, 5 times. The next one would be 7, then 9, then 11. It's just all the odd ones, and that's because of the asymmetry here. Okay? Yay!